Our first finalist today to be Engineer Karina Pierpaoli from the Argentine National Atomic Energy Commission of Argentina, well, supposedly. Skinea, please.
Okay, thank you. I would like to thank the organizers of this special meeting. It's so important to considering the participation of National Atomic Energy Commission in this seminar. It's a pleasure for me to participate of this event too. In the first time, I want to show you which kind of institution is National Atomic Energy Commission. Maybe most of you know about that, but in some cases it's not so not a lot of people know about our activities. The Argentinian Republic has a long-standing tradition in the nuclear industry, having designed and built an important number of nuclear reactors during the last 7 decades, several of which are installed in other countries, not in Argentina. The Atomic Energy Commission is at the same time one of the largest institutions for public research in Argentina, not only for nuclear science, but in most fields of science and technology. One of the activities or some activities that we develop are related with the nuclear technology and the fuel cycle, but also we have a lot of activity in basic and applied research, nuclear technology application, training of human research in our country, and technical support organization of nuclear power plants. We like to say that Argentina is a nuclear-friendly country because our activities are across or along all our territory. In particular, I am the manager of the area of research, development, and innovation in CONEAS, and the activity of this area take place in 3 different atomic centers. One's in the city of Bariloche, and the other 2 are in the Buenos Aires. And the headquarters of National Atomic Energy Commission is in the Buenos Aires city, yes, the capital of the country. Some of the activities that are focused in that moment in National Atomic Energy Commission and are related with the large research infrastructure that in which we participate are accelerators, not only use of accelerator, but also develop technology for accelerators, all the things about energy transitions, working in hydrogen economics, lithium, for example, and of course, nuclear as one of the vectors or solutions for energy transitions, nanotechnology, earth science, astrophysics, and smart systems like detectors, like quantum computing, nuclear application, and materials science. Well, I will try to explain how is our participation in large research infrastructure. CONEAS participate in the different ways, in particular in astrophysics collaborations. For example, Pierre Cubic Hadrons or Andes. We are part of the finance board of these collaborations. Argentina have at least 2 institutions that are finance this project. One is CONICET and the other one is National Atomic Energy Commission. But our activities is all those activities about the development of the detectors, upgrades for these collaborations, and in most of cases operate in the site these observatories or facilities. These large research infrastructure. Some of them are in operational now, are well established in our country. For example, Pierre, the accelerator Tandar, or the research reactor RRC or RR3. And another ones are in progress that are building in that moment. For example, the project Cubic or the Argentinian Proton Therapy Centrum. That is the first centrum in Latin America to be proton therapy for cancer treatment. And the research reactors are 10 that will have their Newton Beam laboratory for science. And some of them are projected now and are looking for funds. For example, Huron, that is another observatory that has fund from United European Union that win funds in November of this year. And the other ones are Andes that not have funds yet, and the project LEMI, that is a facility to look irradiated material, to characterize irradiated materials from RR10. Well, some points about this project, if you don't know anything about that. Pierre project is an observatory that are looking the origins of ultra high energy cosmic rays, volumetric interferometry of cosmology is the project Cubic, that are in the Salta state in Argentina, that are looking evidence of primordial gravitational waves. Other one are hybrid elevate radio observatory of neutrinos that are looking astrophysical high energy neutrinos physics. This is the Heron project that win funds in November. And the other one is Andes Multipurpose Underground Laboratory that are information or looking about dark matters and neutrinos physics. Other projects. Other is about, we have different ways to characterize matters. Some of these way are accelerators. We have a Tandar accelerator that accelerates ions, and the other ones accelerate protons. So with these different particles or beams, we can apply in science in different fields. Some of that are the fields in where we have research in CONEAS, and all these facilities are used in three different areas. Education, we use this facility to training people in this technology and in this field of science. Education, science, and industry. We try to transfer the technology to different aspects of industry and develop products, or to help them to characterize different process or problems that the system have. Something about the new proton therapy, Argentinian proton therapy centers. These centers give proton beams from science, technology, and radiotherapy for cancer treatment. It's the first ones in Latin America. The civil work was completed. Nuclear regulatory license for a startup. These equipment are approved. Scientific and medical instrument was acquired, and the installation of all these facilities is 98%. Why is that number? Is because we need to commissioning the instrument. The license is obtained in November of this year. So we think that in the middle of the next year, in 2026, these centers start up their operations and be available for patients. But these centers have special lines dedicated to science. So we have one line totally dedicated to develop, to use the proton in other areas of science. So we think that physicians for medical application or physicians for other applications can use this facility and increase the knowledge about that applications. Other sources are our reactors that provide us neutrons. We have 3 different reactors. All of that are dedicated to education, science, and industry applications. There are 3 are dedicated to especially the production of molybdenum, to radioisotope productions. LR6 is more dedicated to training and to science. We have some neutron beams instrument in both reactors. We have imaging instrument in LR3 and in LR6 to do tomography and neutrography. And in RRC, which implements a test stations for cancer treatment too, and time of light instrument too. And RR10 is under constructions in that moment. Some details about RR10s. The project is really very advanced. RR10 is a complex for medical radioisotope science and nuclear technology. It's a world-class research reactor. It's a multi-purpose research reactor. It's open pool, it's 30 megawatts with a low uranium fuels, has different purpose. One of them is the use of the development of fuels for the nuclear project of National Atomic Energy Commissions, have facility for in-pool neutrography, has facilities to neutron activations analysis too, and outsourcing implemented to use this the beams that comes through the reactor for scientific applications. The component supply and installation of this facility is 85%. Operation is still training, 85% too. Safety report developments are finished, and commissioning preparation is 90%. Now we are doing the pre-operational test, and we begin with the commissioning of this reactor in the middle of this year. In particular, neutron beam laboratory, we call them LAMS in Spanish, is a research center for development and use of neutron beam techniques for the study of matter. Is in complete suite of this facility is 14 instruments. In the first step, we will begin the operation with 5 instruments, and we project expand this suite at 9 for 2020. Civil work of this facility are completed. There are instrument developed by National Atomic Commissions. These 2 instruments allowed us to develop the technology to design and implement our own instrument in this facility. Other 3 instruments are donated from different institutions of Europe. 2 of them are donated by Helmholtz-Zentrum Berlin. Another one is donated for Paul Scherrer Institute. The facility will have one multi-purpose diffractometer orientated to engineer and material science, one imaging instrument that could produce videos, neutrography and tomography, and In the guide hole, we will have polarized neutron reflectometers and 2 small angle neutrons diffractometers. The 3 instruments donated are in Argentina already, and we are testing them and begins with the pre-integration of their subsystems. This facility will have 7 neutron guides that transport the neutron from the reactor to the guide holes. So we are working in the scientific case of the 4 other instruments. So in that case, we are looking for collaboration in LATAM to decide which kinds of instrument is needed for our regions to implement in that facility.
2 minutes.
Okay, I will finish now. I'm okay. Well, some cooperation challenge that we identified for this kind of facility. If you look at my presentation, we have 2 different kinds of large-scale facility. Now, some of them are experiments that are implemented, and we can use the data of the facility as the observatories. But the other ones, like reactors or like neutron beam laboratory, was a usage-oriented facility. In that facility, we need to think about the sustainability of that. In that case, the owner of the facility is the institution that are responsible for the implementation, the project, and make agreement with other institutions to the governance of the facility. So in the region, we have the challenge to decide how we want to governance this kind of facility, we want to use them, how to promote a real region identity of our science in this kind of large-scale facility. So we invite all of you to be part of these kinds of large-scale facilities that are implemented in Latin America. We think that we can promote integration among scientific associations like Claf, for example, to building bridge to increase the participation of Latin countries in existing or new international collaboration. That's, for example, HERONS that I show you. Now HERON is a collaboration with four countries, Spain, France, United States, and Argentina. But maybe we can increase the number of countries that participate of this observatory. Share experience running national facilities, large-scale user-oriented research infrastructure, and create a network between synchrotron and a neutron beam laboratory that are complementary proof for the access of all Latin American user community. That's all. Thank you.
Thank you. We're going to have a final round with some questions later. Let's go to the next one. Professor Salvatore is now ready. Okay. Professor Salvatore Mede from the CERN.
Waiting for the slides to come up. Sounds good. couple of steps. The three dots which are there, you can say open with uni, you see. Close to the Gemini blue thing, there are three vertical dots. Yeah, if you click there, it should be an option to open or to download. Yes, it sounds good. Yes. So thanks to the fact that there were no slides, I didn't have to give the first talk after lunch. So thank you, Karina, for having taken this on your shoulders on the neutrons. What I'm going to do is to have a few words about CERN as an institution and exactly the role that it has played historically to bring together different countries and regions to cooperate, and how in the last 20-something years, we see that this role is increasingly played outside of the CERN core European set of countries, and how successful has been Latin America and CERN exactly in the last 15 to 20 years. Can I get? So I will go through four things in different level of depth. One is just 3 or 4 words on the research we do with CERN. Most of my discussion is going to be about the collaboration instruments that we use to do that. I want to say a few words because it was cited also by previous speakers on the value of shared research infrastructure for capacity building and how it supports or stops brain drain. Then I have some consideration on the outlook for future scientific cooperation in a Latin American perspective in the activities we have at CERN, both at CERN and in all countries and institutes which are participating. Concerning research, I'll be just very quick. Many people in the room, now that most of the ambassadors have left, many people in the room have a physics background anyhow. So we are trying to answer basic questions about what is the universe made up of and which are the forces that keep it together. If matter and antimatter came out together at the Big Bang, where is all the antimatter gone? These are the kind of questions that every kid with 10 or 11 has been reading a science book asks you, and then you need something so big as CERN to try and answer. And the way these kind of questions are answer is to try to create states of matter which don't exist in the nature as we know it today, but they existed a few hundreds of thousands of years after the origin of the universe by concentrating a large amount of energy in a very small volume by the use of particle accelerator. And the instrument that we are using right now is one of many accelerators at CERN. We have about 100 kilometers of accelerator in function at CERN right now. So it's not only the scientific program at LHC is the most visible, but it's only about 80% of the scientific research where we have a neutron, we have a neutron time of flight, we have an antimatter installation, and so on. So the LHC was designed, was thought of already in the 80s. It was eventually built between 98 and 2008. It took 10 years to build in parallel partly to the previous operating machine. As all the kind of superlatives you want. It's 100 meters underground, there's a circumference of 27 kilometers, is almost as absolute zero because otherwise helium would not acquire the superfluid helium quantum characteristics which allow us to cool the entire machine simultaneously at the same level. Mainly, this is 1,200 dipoles of superconductive niobium titanium magnets, which steer the particles around the ring. That's why it's so big. Otherwise, the protons would not be able to be accelerated at 7 Tesla. Right now, we are in a phase starting in July. The machine will be switched off for 3 to 4 years to be upgraded. And we will put 2 new kilometers of accelerators, which will allow to raise by factor 10 the collision rate. So all the physics that been doing so far is not even 5% of the physics of the data that we are going to collect in the 5 subsequent years. That's a program which will carry us till 2040, 2041. These numbers are important. So you started building it in 98, you run it till 2041. So this is a 50 years program, and then you will have another 10 years to get all the physics out of it. The length of the program is important because this can only be done with long-term commitment at the level of governments, but also at the level of the individual career of the individual researchers of the founding agencies and the institutions. And the program is only successful because there are also all these commitments. So there always a point of you build something which is so big that at the end allows you to do something which lasts in the long term. And these are among the largest running scientific programs you can think of. That is also an interesting aspect. I cannot think of a scientific program that lasts 3 scientific or 4 scientific generations. More on that later. Of course, and that's something that we often say, if you cannot buy an accelerator as it is, because nobody sells it to you, because the technology of the magnets did not exist when we needed to build the accelerator. For the next machine is different because it's an industrial program. And by the action of having to develop the technologies which are missing for the accelerator and the detector, there are a lot of technological byproducts, which are almost all released in the open or are accessible to the CERN participants. Beyond the invention of World Wide Web by Sir Tim Berners-Lee in 1993, there are many applications in medical imaging, hadron therapy, but also the energy transition. Just to give you some point, accelerators for cancer, they've been for the first time demonstrated by 2 CERN collaboration with Italy and with Germany. The third picture, the red thing, is a X-ray of a hand where somebody has a screw. So in a single image with a very low radiation, it's basically a single photon detector, you can do what you normally would do with an MRI and CT scan at the same time. This is not science fiction. This is in production in several hospitals now around the world. That's a patent that we have given to a UK and Latin and New Zealander company. We are increasingly looking at application of our technology for the energy transition, like low loss superconductive lines for bringing ashore high power turbine electricity with special super vacuum for preserving the superconducting capability. Or if you can do something so cold as the liquid helium of the LHC, having a container ship bringing liquid hydrogen, it's easy, it's 40 degrees warmer. So we are also in talk with the shipping industry about this. We are in talk with Airbus for electric planes with superconductive cables, possibly high temperature superconductive. And we also have partnership with hospitals to use anomaly detection AI instruments as we use them for the stability of the accelerator to suggest follow-up for stroke patients which need a specific follow-up. This is just a few examples of the fact that in the moment in which you need to bring a lot of people together to invent a new technology that don't exist, some of those might have an application to society. It's not CERN job to go out and find these applications, but once you have a network of 50,000 researchers around you, somebody will have an idea and will have a connection in a country where this can be deployed immediately closer to society. So again, scales give you an asset that your knowledge transfer in a university doesn't give you. It just, again, from a power of scale. Collaboration is a large part of what I wanted to discuss today. So CERN is, as we have heard, a member organization and also does research. These two things are two separate cooperation mechanisms which need to be clarified. So we have 25 member states and 10 associate member states. Brazil is one, and Chile will be our 11th associate member state a few weeks down the line, and we have no other applications in the pipeline. Altogether, these 35 countries pay the annual budget of CERN, which is $1.2 billion. Is big if you think in terms of university. If you think in terms of a university hospital, is a very small number. Any university hospital is worth 4 times these numbers. All depends how you want to see it. This money, most of it goes back to our member states, because 40% of it is spent in companies in our associated and member states, and another 60% is spent to pay people. So it's upskilling and training, so it's not some sort of black hole. We have 50 collaboration agreements with states and territories, and this open the door for universities and research institutions in those countries to come and do science at CERN. But the point is that it's a club, it's an expensive club. You get something out of it, which is employment and procurement. And thereby lies a strange mechanism, if you think, is that all those countries pay a lot of money to build an infrastructure that everybody can use. Compare these to satellite science. Unless you put the money in the satellite or you have the rocket, you don't get the data for at least 3 years. And this is a strange model. People say it's a very European way to do things. And this has served as well, because it started with 12 countries. And you can see that now we are covering, we have relations, scientific relations with about 80 countries, 80. Altogether, the member states pay the budget, but the infrastructure is a open research infrastructure, which is used by about 13,000 researchers, which occasionally come to CERN. The entire size of the community is about 50,000, but only those who occasionally need to physically come at CERN, either for a meeting or because they're installing some hardware or because they're taking data, are the ones that we register and record, but we know that the community, just looking at the number of people on the paper, is much larger. I cannot not show this picture. Unfortunately, it's my face on the bottom. I don't know if you can move the thing away. That's another historical photo. This is from the very first meeting. Actually, this was in Copenhagen when CERN was established. First thing you note is the diversity. Everybody in the room is like me, is white, is European, is in mid-50s. We have not improved much on diversity yet. People are smoking. This maybe we have improved on this part there. But the words that were written in 1953 in our founding convention, and especially on the discussion we were hearing before from our colleague from CDPF, they still resonate today. So what these people were doing, they were doing diplomacy for science, bringing those countries together, as Ambassador Eugenio was saying, to put together a cooperation mechanism which allowed to do research at a scale that no country could afford alone, as our ambassador from Chile was mentioning earlier before. And in a sense, as the ambassador from Mexico was commenting before, to reverse the brain drain that, in addition to the persecution of Nazi Germany, had seen many Europeans, Enrico Fermi is a case in point, flying to the United States. So what they decided to do altogether was to fix the brain drain problem, which we've been discussing this morning, to bring together countries so they could get stuck together and do science together and not spending their time fighting together when the governments of two separate agencies, they change polarity. It was Carlos was mentioning before. So the irony is that most of the things that we've been discussing in this room are problems that seem to be natural to mankind, because they were there also in 53. And one possible solution, quite idealistic, which seems to have worked out, was to create CERN, among other, for having purely scientific and fundamental character in research, no concern with work for military requirement, The results of the experiment had to be published or made generally available. This was Open Science in 1953. CERN should also organize and sponsor international cooperation, including cooperation outside the laboratory, and in particular contacts between an interchange of scientists, dissemination of information, and the provision of advanced training for research workers. As we were discussing with Rock earlier today, these are all the intangibles that CERN gives to its member, in addition to whether a company gets a contract or a person gets a job. So that's a deep point of reflecting on the value of a scientific infrastructure, because it gives you also all these science for diplomacy. So the people in the room were doing diplomacy for science. Now that we have this tool, we are actually doing all this stuff, which is even in the world of today, with some challenges that CERN has had in the last 3 years in this respect, the opportunity to promote contacts between institutions, persons, and areas that would not have been in contact otherwise. So we are a user facility. These are where all our users come from. What you have to figure out is that the red band, these are the number of users from the 70s to today. The red are the users from the CERN member states. And you see that this number goes down and down. Even though we have more and more users, the fraction coming from the member state is now about half, because about the other half comes from all over the place, which means that the idea of having an open infrastructure everybody can use is a smart idea, because you get twice the brains to get physics out of your data than you would have had if the physics was only limited to the ones who were paying for the machine. So the model has served us very well. In fact, we can afford 4 large experiments observing the collisions. If you only had European resources, we would have built this big machine and only had 1 experiment. We can do 4 times more physics, thanks to the fact that the model is an open model. And there are now 900 research teams from 77 countries just working at the Large Collider, the LHC, 110 nationalities.
Professor, please, you have 2 minutes.
2 minutes. I have an entire other talk to give, so we skip. So if I have 2 minutes, I have to say very few things. So this is something I want to say. At the moment, we have 12 Latin American countries which have a bilateral agreement with CERN, and in total 300 users from 46 institutes. Just we added yesterday formally an institute from Honduras, which is a relevant point. We still have a cooperation agreement which are around from a while in the case of Paraguay or Bolivia, or recent in the case of Uruguay and Guatemala, where we hope to see more scientific cooperation. We can skip because I ran out of time. This is something I want to show. There are 2 lines on this plot. One is a blue line, one is a red line. They are the number of people coming and working at CERN from 2000 to today. You have to appreciate the slopes of these 2 lines. So the number of users, the blue line are all the users working at CERN. The number has doubled in a period of time, which is 25 years. The number of users from Latin America is small. There are like just 300, but this number has gone up by factor 7 in the same period. So we have now 7 times more researchers from Latin America working at CERN. Most are from the 4 largest countries with the 4 largest scientific communities, Brazil, Mexico, Chile, and Colombia, but there is a longer tail. One point that I wanted to make is the fact that on average 30% of people working at CERN, that their university is sent to do research at CERN, they come from another country, not the country where their university is. So there is a functional brain drain in this. The number for Latin America is 50%. So there are a large amount of Brazilians and Mexicans who have left their country, as you know very well, and with particle physics staying elsewhere. But we also see some positive signs, and this starts to change. In the case of Chile, we start having a lot of Chileans who are going back to Chile and do physics in Chile. That's the case also in Costa Rica, is the case in Honduras. So what we observe is that by the fact that a university participates in a research program at CERN, and a postdoc in that university, if it has enough, she has enough resources to do this kind of science, you take away one of the main incentives to leave. Because if you can do the same science staying at home, occasionally working at CERN or occasionally working with your colleagues, many people prefer, and the data show that in the multiplication by factor 7 of resources, to just stay and work there, because those numbers are not people who have come out of the air. They were in the US before. Now they prefer to stay at home. Capacity building, I don't have much, so I will skip this part. I have to skip, so we skip one more. We skip one more. We skip one more. And I want to come on the outlook for scientific cooperation with Latin America. Now, there are one program which is we are running now is upgrading this accelerator so that we have the high luminosity, so more collisions, LHC. Right now, 2 detectors are being upgraded. We are designing the upgrades of other 2 detectors. And this will be hardware which is designed now, will be built in next 3 years, 4 years, and will be installed in 2030, and will run till 2041 and before and beyond. Right now, teams from Mexico, Chile, and Brazil, and Costa Rica are actually involved in designing pieces of hardware for those new detectors. This is an opportunity for regional cooperation because there are many other teams in these collaborations who don't have the know-how, the resources, or the possibility to create hardware projects, whereas Brazil is perfectly located, as the existence of Sirius and other programs demonstrate, to be a leader. So one thing which can happen is to coalesce in 1 or 2 hardware projects, which can be silicons or can be calorimetry, whatever, and have a first Latin American project. The fact that CNPM is contributing to Dune like CERN is shows that Latin America can do it. And that's now. The next step is that we are already looking at the next possible project for CERN. We are midway through a phase of prioritization from the scientific community of what they might want to build. We expect that the proposal will be put forward to build a 90-kilometer accelerator. We call it the Future Circular Collider. Eventually, we'll change the name because it will not be future, it will be a fact. We already have a potential industrial partnership with CNPM in Brazil. As also Fernando Quevedo has said before, there is no reason for which we couldn't coalesce now in Latin America like-minded person to pick up projects which don't necessarily need to be big hardware. They can be physics simulations or data science, and start to have a cooperation within the region, because the people are there and the capacities are there. Just what is bizarre is that very often 2 persons from Latin America, or even 2 persons from Brazil, to cooperate, they have to come all the way to Geneva to talk to each other, and we are trying to change this. As I had to skip a few things, I will conclude with just some observations, which I just said exactly in the last few sentences. We are observing a Latin American moment at CERN, 7 times more users, people who build things for the time being in Brazil and in Chile, somehow in Mexico, incredibly high level of students because the public university of the continent are excellent. And given the demographic tide of the continent, once you get to graduate in physics in a country which has 200 million people, you make it to CERN, of course you should be pretty good. You wouldn't have made it till then. There are a lot of programs that we run to enhance also with Claf capacity building, community building, which are working because we see the people. This also results in more countries getting involved at the institutional level. I was making the case of the last 2 countries we signed an agreement with, which is Uruguay and Guatemala. We hope soon to see funding for particle physics in these regions, and the membership of Brazil, also the membership of Brazil and Chile. So I do believe that there is a one-in-a-generation opportunity to create a research program in particle physics in Latin America, coordinating a few universities and institutes, each with their own funding. I don't believe in regional funding, but I believe that if a few universities have a vigorous backup in their countries, where somebody is a bit weaker, somebody else can take over, and vice versa. These are, after all, 20, 30 years program. I hope that this can, how far Europe has come with its own 1953 fantasy can give you inspiration to take this opportunity, which is yours to take, because let's not forget now, CERN is also a bit of a Brazilian national laboratory. It only happens to sit in Switzerland, and so it's going to be also a bit of a Chilean laboratory. It only happens to sit somewhere else. Sorry if I overrun of 3 minutes.
Thank you, Professor. Our next talk will be from Professor Antonio José Roque. Não, Edson, você, which is the director of our largest facility or group of facilities, not only cities, but several national labs there.
Hello. Well, good afternoon. Thank you for the invitation. I'll talk about, come back here. I'll talk about CNPEM. We have people here that know, some of you know CNPEM. Aragão was Director General of CNPEM a few years ago. And that's the, so big shoes to actually for me to fill, but I think we've been doing fine. Yes, Aragão. So CNPEM is, as Ruben said, of course, a highlight is Sirius, the only synchrotron light source in Latin America. But we have other labs. I will show some data about this, the users from Latin America to these other labs. So we have, as a highlight for this community here, the nanotechnology lab. But we also have biosciences and biorenewables lab, and also a lot of engineering and instrumentation, as I will show. And this is important for interaction, for example, with the CERN. We have a management system that, even though we receive resources from the Ministry of Science and Technology, we are a private institution that signs a contract with the Ministry of Science and Technology to operate this complex. So we are what it's called, Rubens mentioned before, Organização Social. So we have close to 1,250 employees these days, and if you count students, trainees, postdocs, and outsourced personnel, close to 1,900 people. And we have recently started a faculty, bachelor's in science. The mission is organized mainly in 4, let's say, axes here of activities. Open facilities, so we have some facilities that are unique in Brazil, and you have to have, let's say, systematic ways for any research from Brazil or other countries to access the facilities. We do internal research, R&D, but usually coupled to strategic programs of national interest defined by the Ministry of Science and Technology or other ministries. Usually in agriculture, important thing in Brazil, health, energy, new and advanced materials, and environment, more and more environment. Looking at biodiversity, for example, in Brazil as an important resource. And then we have to support innovation and have activities in education, training and outreach. I'll show some data about this, the open facilities connected to the users from Latin America later on. So the birth of CNPEM was the dream of some people from CBPF, as was already mentioned, that had the idea of building the first synchrotron light source of the Southern Hemisphere using Brazilian technology. Silon Gonçalves da Silva, some of you might know him, was the head of this project, very important for, I would say, science in the country, as well as Ricardo Rodrigo and Aldo Krajewicz, who passed away a few years ago. So it was a turning point in the Brazilian science in the sense that a big facility has been decided to be built entirely and developed in Brazil. And the most important thing, in my opinion, actually allowed us to actually build Sirius is the fact that the training of human resources. This is fundamental, and we've been continuing to do this because that's the only future. But it was not a competitive machine at the international level. So once we have actually a mature community of users, they started to demand a more competitive machine. That's what gave rise to Sirius. Sirius today is a competitive machine. It is one of the few fourth-generation synchrotron light sources in the world. Today, until, let's say, beginning of this year, there were 3, including Sirius. Now, by the beginning of next year, end of next year, there will be 6. Argon is already operating. PSI has done also an upgrade of its accelerator. Argon did an upgrade of its accelerator. Now, PSI has done also an upgrade, and China has built HAPS. By the end of next year, there will be 6. The first one was Max 4, and then came at the same time SRF and Sirius. So it's, I would say, an amazing fact that you can actually have the capability of building a machine that's completely is competitive worldwide, came before the United States, most of the countries in Europe, even before China. And that's because 40 years ago, there was a decision to actually starting to do this kind of development. It's operating these days with 10 open beam lines, covering a lot of different fields. 2 more are being commissioned. Probably by end of next year, beginning of next year, 3 more will come. So we have already funding for total of 24 beam lines. So 14, those are the ones that we are finishing connected to what we call first phase. And we have started already building 10 more new beam lines within this program of President Lula Novo PAC. So by 2028 or 29, we should have 24 beam lines directly connected to researching with Sirius, but we're also building with resources from Novo PAC. Our resources come from FNDCT, connected FINEP, where Aragão is the executive, how do you say, executive secretariat of FNDCT. So we're building Orion. Orion is the very first maximum containment biosafety laboratory, BSL-4, also in Latin America, and will be the very first in the world connected to a synchrotron light source. And the reason why we plan to connect this to a synchrotron light source, because this fourth generation light source, they're very good at providing imaging, 3D imaging, and with both for inorganic or organic materials. So the whole idea is to have 3 beam lines, one of higher energy that you can do tomographic imaging with high resolution of live animals, and so follow the disease with, let's say, a high resolution. Then a second beam line of lower energy that you can do 3D imaging at a cellular level, a cellular resolution of tissues and small organs. And then finally, one beam line of lower energy dedicated to do 3D imaging, tomographic imaging of single cells, where we are planning to actually be able to visualize viruses inside the cell. So I have the capability of going from cells, looking at the virus inside the cell, all the way to animals. So coming back now to the open infrastructure, that's the axis 1 of our mission. We have synchrotron, of course, as a highlight, but many other facilities. Have close to 40 open facilities, from electron microscopy all the way to a pilot plant for biorenewables research. So some numbers from users, for users from Latin America. So I asked them to collect all the users that came from some country in Latin America between 2021 and 2025. Why these years? Because the beam lines of Sirius really started to be operational by 2021. So the first beam line was 2020, and it was in the middle of the pandemic. In 2021, we had 6 beam lines total. So I separated here if facilities connected to the biosciences lab, facilities connected to LNLS. This is basically Sirius, and then facilities connected to the nanotechnology lab. And you can see that nanotechnology lab and the synchrotron, they sort of dominate. And Sirius being the most used facility, 288 users from Latin America, and nanotechnology, 161. And you can see Argentina is our largest user, but it's interesting that Chile, in both the two most used facilities, you have Chilean users with a significant, let's say, proportion here, especially for Manacá. Manacá is a beamline for structural molecular biology, and the largest actually bar here is cryo electron microscopy, so also used for structural molecular biology. So as you can see, the largest the fraction of usage of CNPEM by Latin American users is on structural molecular biology. I would say it's a very competitive and mature community in this region. And for example, we're signing an agreement with Uruguay now, connected to this area of biosciences. So it's an interesting, let's say, future. But Carnaúba, Caterete, and Paineira are more, let's say, regular physics or material science beamlines. So those are also heavily used, and ME is molecular electronic microscopy, also is the second largest in the nanotechnology. So it's about 5% of the users are coming from Latin America. By year, so we can see it has been increasing. It's connected to the fact that also Sirius is including more and more beamlines each year. So this number will only increase as time goes by. As I said, Argentina by far dominates this use. This is a very interesting graph. I asked them to compare the old machine UVX with the new machine Sirius. And so I looked at the 3 last years of operation of UVX, 2016, 17, and 18, and the last 3 years of operation of Sirius, 23, 24, 25. And I asked to compare the number of users coming from Latin America compared to users coming from any other country in the world. I'm not counting the Brazilians because by far the sum is something like 15% from other countries and 85% from Brazil. So I'm comparing this thing. So as you can see, UVX was a factor of 2 or more when you look at the foreigners that were coming. With Sirius, you have already see an inversion of this. So of course, UVX was not competitive, as I said, when you look in other countries in the world, and now Sirius is. So Sirius is very attractive also to other countries. But that's something that we should pay attention because not only for the Brazilians, because we have to be careful not to let all the foreigners dominate this, but also in Latin America, we have to maybe try to be more competitive. I'm not saying you need to necessarily say that the other countries shouldn't come, but the question is, why are they managing to actually get proposals that are more competitive? So that's an important message, because always when I was trying to actually talk to the community, especially the users community, I always used to say Sirius is not a machine to do much faster the same thing that you used to do at UVX. Sirius is a machine to do some science that you could not do at UVX. So this requires that you think in a much more competitive kind of research, which is good. Yes, it means that we have an equipment that is competitive worldwide. And so many programs can be actually done to use such an equipment to, let's say, increase the capabilities of the science in the region here. As I said, interesting, most of the users, they are connected to biological sciences and biotech, and they don't call what they do physics. This is sort of a self-classification. They say which area. We have a certain number of areas, and they say the number of areas. So they say they do material science and nanotechnology much more than do physics over there. So that's an interesting thing. Okay, so now I'll talk about engineering instrumentation. As I said, because we had to build the first synchrotron like 40 years ago on our Sirius, a very competitive machine, we have managed to actually develop a very competitive instrumentation engineering group. Those are the accelerators. This is the linear accelerator. Then you transfer to the booster, you increase the energy to 3 GeV. So it was 150 MeV at the LINAC. Then you transfer, goes to 3 GeV. Then you eventually transfer this to the storage ring. Is a half kilometer divided in 20 sectors, and you keep the electrons running at 3 GeV. And in some places, you deviate the trajectory to actually collect the photons that are emitted in the tangent in the so-called beam lines, and that's where the experiments are done. If you look at the parameters of the accelerator, they are among the best of comparing any synchrotron in the world. So it's top 5 as when you compare. And this is our longest beam line. It's extremely sophisticated beam lines, 150 meters. It will have 2 experimental stations. The first one has been operating for a few years. You have been able to reach a resolution of, let's say, 15, 20 nanometers. And we're finishing the commissioning of the second experimental station. And we'll be able to reach a resolution, spatial resolution of 1 to 2 nanometers with a variety of kinds of experiments, including 3-dimensional experiments. I imagine that if it's not the only beam line in the world that does that, it's one of the very few that can do these extremely competitive kind of experiments. And then we had to develop all these things. Some of the equipments we had to actually design ourselves. We have many patents. An important thing, this has been done with a variety of Brazilian companies. So this was a program. FINEP was very helpful also, FAPESP at some point. But the whole idea is that the flexibility of the managing model allowed us to do a lot of different kinds of contracts, trying to engage Brazilian companies, from big companies like WEG to startups that today produce X-ray detectors. Now coming to CERN finally, these capabilities, because CERN, you have the detectors and you have the accelerators. And we have capabilities connected to building accelerators, so it was natural to actually interact with CERN. Actually, CERN has been a partner since the very, very beginning, of the idea of building synchrotron in Brazil. And so we have managed to sign an agreement with CERN, a formal agreement in December 2020, before Brazil became associate member. This has been renewed maybe a couple of times, yes? And the very first project was, it was clear that we have been successful. We have now the capability of building normal electromagnets, but we had never built a superconducting device. And CERN is among the most competent places in the world to build this kind of devices. So the whole idea was to interact with CERN to get technology transfer. So we have managed to actually build superconducting device. It will be able to generate 6.8 Tesla or 6 point something Tesla. So more than twice the amount of a magnetic field. This is very important to be able to actually get hard X-rays. And Salvatore always tells me that south of Dallas, this is the very first place in the world that actually builds superconducting device that will be installed next year at Sirius. Hopefully it will work. But at least the people from CERN, I think they were very happy also with the success. And the second project, Salvatore showed the importance of, let's say, working with health. The capabilities you have to build everything that you build there at CERN and that we built here can be applied to health. And so we engage, and we think this is an important thing in the country, and we have started a project to actually build first a proton accelerator and using an interesting RF cavity, a design from CERN. They helped us to actually learn this, and we have managed to actually adapted this to our amplifier frequency. And then we built this as a very complicated machining and development. And we have managed to actually get proton beams this year. And we're already moving to the next phase to actually increase the energy. So we have reached close to 1 MeV. So I say this is like UVX at the very beginning, so we can move faster now, but also for protons. And finally, Brazil became an associate member. And because of all the connections that CNPq has with all these companies, we are supporting the activities of the Industrial Liaison Officer, ILO. So CNPq is heavily involved also with the interaction of Brazilian companies with CERN. And finally, Salvatore already mentioned the next big project. Of course, there is the upgrade now. I don't have time here. We are being involved also on the development of some parts of detectors at CERN. But there is what I think one of the most interesting and fantastic opportunities due to all these developments. FCC will have this close to 100 kilometers circumference, and you need to have a transfer line, I imagine, between LHC and FCC. Is that correct? Okay, but one of the injectors towards the FCC. And it's a 5 kilometer in length accelerator structure. This is 10 times bigger than Sirius. And the magnets that we have developed for Sirius with WEG, they might be used for this. So we have just signed in November at BPF, Ulysses was there, an agreement, Salvatore was there, an agreement with CERN, with FCC, to develop the first prototype. I think we're going to build the very first prototype, and we're extremely confident that we might be able to build many more components of something 10 times bigger than Sirius. This is, I'd say, some very interesting perspectives. Thank you.
Thank you, Zé Roque. We call him Zé Roque here in Brazil. Okay, our last speaker for this panel will be Professor Dr. Norbert Kucherba. It's correct the way I did spell. The head of science organization activities of the Joint Institute for Nuclear Research in Dubna, Russia. Please.
Yeah. Thank you very much, Ruben. Let me start by saying how grateful I am for receiving the invitation here. Thank you very much. I'm really honored to be at the same table with all of you. Also, at the beginning, it might appear I'm falling a little bit out of the pattern here by representing the institute that it's on the other side of the world. But I'm going to show some slides and try to convince you that we have many common things. So next slide, please. So first common thing with Claf, I just learned a few hours ago. So JINR was established in 1956 on March 26th. So exactly the same, very same day as Claf was, in the different year, but at least that. Anyway, so pretty soon we will be celebrating 70 years. At the moment, we have 15 member states, and we recognize three different levels of membership. So it's a full membership, associate members, and the partner states. And so what's important here is that at least 3 of the countries of Latin America are among these member states at the different membership levels. Cuba, well, I will be talking about it more later on. Next slide, please. So the organization, the management of the organization of the institute is based on the multi-level system, having different management and advisory bodies. What's important to underline here, next slide, is that among these, next slide, please. In the members of these different bodies, there are scientists and people from all around the world, even going beyond the membership countries. And what's important, there is quite a few of them from Latin America region. We have a member in the Scientific Council from Brazil, one from Argentina, at least one from Cuba and Mexico. And in other bodies, we have also some members from Latin America countries. Next slide, please. So Cuba. Cuba is a full membership country since 1976. It went through some good times, some bad times, but Cuba stays with us to the very days. And we have been always thinking there's a very active collaboration with Cuba and Cuban scientists, and especially recently we were, well, some 5-10 years ago, we were thinking about Cuba as a gate to Latin America countries for JINR. Next slide, please. In the recent years, there has been, however, let's say, more active countries from the region. First of all, Mexico, who became a partner state in 2023, when we have signed agreement between the JINR and the government, well, the agency, CONECYT agency of the Mexican government. So there is very active collaboration. We have established a joint collaboration committee that is regularly making calls for projects, and so there are common projects between JINR and Mexico. Next slide, please. Another very active country from Latin America is Brazil. Of course, actually, Brazil has had a member in the Scientific Council of JINR already in the last century, let's say. And recently, starting in 2021, I think there have been quite a push for initiative for the collaboration between Brazil and JINR. There have been several visits at a high level, so representatives of MCTI have been visiting JINR, representatives of JINR have been visiting different organizations, including CNEN, CNPEM, and other places in Brazil. And finally, in May 2025, so this year, just about half a year ago, there has been the agreement signed between JINR and MCTI by the Minister of MCTI. Next slide, please. So these are the two most active countries on our list, let's say. But we do organize and we do have contacts with the region of Latin America in general. What we do already, we have done it already twice. We have organized the International School on Nuclear Methods and Applied Research and Environmental Material and Life Sciences for Latin America. They have been held in Cuba for the last 2 years. And actually, the plans are to organize the 2026 session of this school in Brazil. Also, we organized JINR days in Latin America just on last 2 days. Secretary Andrea Lage took participation in these days on Cuba, which were happening there. There was also the another high-level meeting of JINR being held there. Next slide, please. This is about the collaboration that we have already active in the area, in the region of Latin America. Now let me go to the second part of my presentation and talk a little bit, show you what we can offer for the collaboration. Joint Institute for Nuclear Research, as the name says, is focused on the nuclear physics, but it actually goes beyond just nuclear physics by applying the methods of nuclear physics to other areas, all the way to biosciences, life sciences, and so on. But let's start with the sort of a flagship of our institute. So institute consists of comprises 7 laboratories, which are very, very different, and pretty much each of them is focusing on a special area of physics. So the first of them is the physics, is the laboratory of high energy physics, where the large research infrastructure is nucleotron-based ion collider facility. It's a facility, well, sort of similar. It's looking at the similar physics as the accelerators at CERN. It looks at the complementary area of the matter and energies of the matter at the beginning of the universe. This is the NICA, and this is actually a place that gave the birth to the technology of synchrotrons. So Wechsler, this laboratory is named after Wechsler, who actually discovered or established the way to do the synchrotrons. Next slide, please. Another laboratory that works in the low energy nuclear physics is known by creating new elements, producing and studying new elements. So there is a facility called Super Heavy Element Factory that has been built previously, but this laboratory actually have been working in this area from the very beginning, and it's known by creating elements like dubnium, that was called after Dubna, which is the city where the institute is placed, and all the way to the element 118, which is the heaviest element at the moment, and named after, it's named Oganesson, named after the scientist who still lives and works at the institute. It's actually only the second case in the whole history of the table of the elements where the element is named after the living scientist. Next slide, please. Another laboratory, Frank Laboratory of Neutron Physics. That's actually my laboratory where I'm coming from. We have the nuclear reactor, and it's a very unique nuclear reactor on the world. It's a pulsed nuclear reactor. It produces neutrons in pulses, well, around the reactor, there is 15, well, roughly, it depends how you count them, 15 instruments that are used for studying the properties of the materials, new materials at the extreme conditions. So most of the experiments are used for studying the condensed matter, and properties of different materials. Another few instruments are used for studying the nuclear physics, the basic the reactions that involve the neutron, and studying the neutrons themselves. Next slide, please. Another laboratory, a laboratory of nuclear problems, have built a detector for detecting the neutrinos. This is the detector that is built not directly on the site of the institute in Dubna, but it's in the lake of Baikal in Russia, and it's called Baikal GVD gigavolume detector, where the water of Baikal Lake is actually used as a detector for neutrons. And so every year we are installing new and new optical modules we submerge them in these waters and use them for detecting the neutrinos. The idea is to reach volume of 1 kilometer cubed in 2027. Okay, next slide, please. So we have a lot of different accelerators on this site, neutron reactor, and so we have different sources of the different kind of radiations, and we use them for studying the basic physics, nuclear physics, and the high energy physics, the material sciences. But we also use these different radiations for irradiating or studying the effect of the irradiation on the life systems, studying the effects of radiation on the biology, and so yeah, I guess that's enough. Next slide, please. And of course, in addition to having all of these facilities, and not only to addition to it, but it's absolutely necessary to have the supporting laboratories. So one of the laboratory in the institute is the Laboratory of Information Technologies with the supercomputer, and also being part of the grid networking that is used for the experiments in the institute, but also the different experiments around the world. It's a part of the world network. Next slide, please. Another unique laboratory that we have is the Laboratory of Theoretical Physics, where we have in one place about 200 theoretical physicists.
No,
and so it's yeah. Got it. I'm just about to finish. So we have in one place, so it's another facility, you may call it, where we have not the artificial intelligence, but the actual intelligence, about 200 intelligent people sitting together and doing the calculation. Next slide, please. And finally, we have the university center that provides, that offers different training programs for the students, all the way from bachelor's, master's, PhD thesis, and so on. Next slide, please. And yeah, is that I invite everybody to come to Dubna and do science in Dubna. Thank you very much. Next slide, please. Thank you for your attention.
Thank you. Very impressive, structured as well. Well, I have to finish, but to finish our panel, I will make a question, general question, as we are. My former shared asked a similar question, but how, with all these different infrastructures, CERN, Dubna, at TNPM, at the Argentinian facilities with nuclear and neutron, how can we improve the collaboration and the interaction? This is the question I would like you to answer. Maybe the first one could be Karina, as following the orders we have with the speakers.
Yes, I think that in Latin American, we don't have enough experience in the collaboration between us as a regions. We collaborate all the time with activities with European laboratories or United States laboratories, and as a country, an individual country. And now we have large scale facility in our region, in our territory, but we are not looking together as a whole things, a partners in the sustainability and in the put money in the same infrastructure together all the countries. So I think we need to push our governance or the key people to take the decisions about where the funds go to push or to increase the capacity of our large-scale facility. And the scientific society could bottom up talk with the people that are decision makers to orientate their decisions in that directions.
Thank you. Professor Salvatore.
As I mentioned before, you can see how fully integrated, in the specific case of particle physics, that everything else is now the European research infrastructure. And the reason for which European universities and teams are so integrated is because they did a lot of science together since very long. And now it looks to me that we are trying to do the same, we are trying to achieve the same target. So again, with the experience that I have, I can observe that there are a few places in Latin America. There are a few university-based laboratories in Chile. There is a BPF, SMPM in Brazil. And if you can install the accelerator, you bought the accelerator from Belgium, but you are installing and running it yourself. So this is not turnkey, you are doing the work. Obviously, there are the capabilities to do something large scale. From my personal perspective and my institutional perspective, the opportunity would be for groups from Latin American countries which are already working in a project at CERN to take the responsibility of building something together over 5 to 10 years. Some years somebody has more money, some years somebody has less money, some years some government change, they don't want to talk to you, then they change again. This is organic. But if you have a project which is long enough, you can spread these problems and you can try to leverage these 4 countries, which are very stable countries with an installed scientific capacity, to actually try to build something. Because that's exactly what we did in Europe and we integrated.
Thank you. Zé Roque.
I think, as Karina said, now we are starting to have some competitive, larger scale infrastructures in South America. And this brings the opportunity to actually try to connect the communities to these infrastructures. I've shown that as an open facility, we have been already receiving 5% roughly of Latin Americans there. So, but that's a natural thing. So how can we actually change this to another level? As you also saw, we are losing, let's say, space here to the other countries when they submit to cities, for example. So I think there are a few things you can do. So you can have, let's say, small scale projects that you can have calls for mobility as usual. You can have Karina and myself, for example, can sit down and try to structure common calls for projects that will use both neutron and synchrotron, for example, to try to bring the 2 facilities together. Or what I think is more interesting, is if we can structure programs that look at regional problems. For example, the region has many common, let's say, problems and common opportunities. And these facilities, and that's the challenge from our side, is to show how you can connect these facilities to help solve these problems. I'll give an example. We have this regular access of cities. But one thing that I was always discussing with Harry, the director of the operation of Sirius today, is if we couldn't have a different kind of call connected to a specific Brazilian problem. So we identified together with Embrapa. Embrapa is a large, let's say, also research institute distributed all over Brazil that works on agribusiness. We have discovered that there is a problem with the region, important region in the country of what we call is a very compact soil. So you wet the soil, it becomes a regular soil, but once it dries up, it becomes like a rock. And nobody understands why this happens. And the first, let's say, way to actually try to mitigate is understand why this becomes so compact. It turns out that, and then we have imagined that maybe Sirius could be helpful for that. So we reserved some percentage of beam time of certain beam lines. We, together with Embrapa, selected a group of researchers that we they could be involved in this kind of research, organize a workshop together. Within this, let's say, 2-day workshop, they have managed to identify some hypotheses. And then we schedule the usage of the beam lines to try to address this hypothesis. This has been going on for a bit more than a year, and we have almost completely understood what is going on. So this is sort of a mission-oriented kind of access to the facility. So if we have managed to identify, of course, who will identify this? It needs to be the governments. They need to actually to see that you can catalyze the interaction. And why this is important? Because you need to convince not the Ministry of Science and Technology of each country. You need to actually convince the people that decide the money that goes to the Ministries of Science and Technology. And they have to see that these equipments, they can help to solve the problems that society needs to be solved. So you have climate change, you have biodiversity, you have many problems. Here, agriculture is a strong thing. So we could maybe try to identify some common challenges and see how we can engage these infrastructures to actually help solve this problem. So I think that could be a very interesting, powerful way actually of boosting the collaboration in the region.
Thank you, Zehorki. Now, Dr. Norbert Kucherba.
Yep. So it has been said already several times that these facilities absolutely have to be part of the open science. They have to be open, and so I believe they need to be connected. There has to be some kind of network of these facilities, because you know, at some level we all compete between us. We compete, especially we compete, for example, for financial support in our governments or whatever, but we may gain much more if we are somehow unified and not compete for this money, not compete for the support, but go for it together. Pretty much all of the facilities that have been mentioned today are not focused, are not exactly the same. They are complementary. So having a network would be only a natural thing.
Yeah, now I can open the.
Can we?
Yeah.
Okay.
Right, Ulysses.
So let me make a comment on some things that IUPAP has organized for many years now. IUPAP has working groups, some of which exist for many, many years. And now we've decided to change them into a new type of structure. We will start to call them standing committees, But the oldest one is ICFA, the International Committee for Future Accelerators, was created in the early 60s to discuss exactly future accelerators in high energy physics. And what IUPAC provides to the community of not of users, but the people that are in the leadership of those, in the governing structures of those types of facilities, to come together, to know what their plans are. That's, for example, where CERN meets China. And that's a neutral venue that we provide as IUPAP. And right now, the chair of the Commission of IUPAP on Particle Physics is a Brazilian guy from USP, it's Marcelo Munoz. So there is an opportunity, and I am from Latin America too. So I think that there is an opportunity to try to bring more partners from our region into this type of neutral collaborative network, venues. There is another one on nuclear research, and there is no participant from Latin America. It's the International Committee on Nuclear Cooperation. And there you have JINR, and you have many other partners from Europe, the US, etc. So maybe one possibility, and since now we are redefining a little bit these structures, there is an open possibility of bringing in some partners from Latin America. So I will look into that. Plus, we created a new working group to look into the possibility of creating new standing committees, for example, in fusion facilities. We are about to create a standing committee. We've already approved it at the GA months ago on neutron research facilities. The people from the US are trying to bring together the potential partners. But of course, we can send invitations to all IUPAP's members to submit proposals. So that's an important venue, I think. And you should, I don't know, use the fact that people from Latin America are in positions there in IUPAP that can induce change.
Thank you.
Ruben, I also would like to make a very quick, 3 quick comments, just not to lose this, and then we go to the next panel.
Or you're the owner of the meeting.
Well,
I would like to make a comment before or after you, but it's okay.
No, it's just, first of all, to pick up what Silvina said, because she mentioned ICFA explicitly. And I think this is because ICFA is a node committee, but for some reason, Claf indicates a Latin American representative for ICFA for the committee. So it might be something interesting to understand if this could be normalized or regularized in the sense that in these committees of the IUPAP, which are very relevant for discussing global matters of cooperation in physics, Latin America could have a unified voice, and Claf could be a natural organization to recommend it, select this person and then recommend through the input of the community this unique Latin American voice that can help organize things. The other 2 comments that I would like to make is that first related to the presentations of Karina and Zeroke, the fact that we have been discussing since a couple of months ago or a few months ago, the idea of doing something with CENPEN and particularly Sirius, which would be an ambassador program, in fact, expanding the program that you already have to Latin America, so that we can also help to increase the reach that these facilities have in other countries of the continent. And when discussing these things with Karina, she also mentioned that this could be an interesting thing to reproduce to Argentina. So there are experiences from each side that can be transcribed to the other very easily. And when it comes to Latin America, Claf can help find the right people and organizing the community to bring together to realize this. So again, this is something which I find very promising. And of course, that's why we are having this panel here. And I cannot leave this panel close without thanking the contributions from Salvatore and Norbert, which I think are examples that, as they said, will lead us in trying to build similar things as those that have been built in larger organizations out of the continent. And also to thank them because they are coming from very far. So Norbert's coming from Moscow directly to this meeting, and Salvatore from Geneva. So thanks for the great effort of,
I would like to
being
make
here
a
with us.
final comment as the chair of this panel, which is, it seems to me that sometimes we from Latin America should learn with Europe and maybe make a commission, or maybe if Mercosur was different, had a different structure, we could have a scientific commission on Mercosur and decide some common things or common infrastructures, discussing before each country starts to do for himself, you know, something maybe we should learn from them. The only thing, so it's just that. The other things are about Claf is for the next panel. Thank you, everybody. Thank you to all speakers. And Ulysses, again with you.